Hi learners, welcome to DHILK. In this video, we are going to master everything you need to know about diazonium salts. So we will discuss every important concept in detail in a simple, clear and step-by-step manner. So watch the full video. So let's get started. What will we cover in this video? We will talk about the structure and nomenclature of diazonium salts. Then we will move to the preparation parts that we have discussed already in another video. If you guys didn't watch, go and watch that video. Then come back here. We'll just recap the preparation. Then the physical properties of diazonium salt and the displacement of N2. There are different reactions. So we will discuss those reactions by displacement of N2 or retention of diazo group. Then finally we will discuss the synthetic importance also. So let's start our journey. Within this video we will cover all the topics that you have to know about the diazonium salts. So let us start with the section 1, structure and stability. So diazonium salts, we know what are diazonium salt. They have a general formula R into X. Here R is the aromatic compounds and X is the counter ion, and X can be any type of counter ion such as chloride, bromide, hydrogen sulfate or fluoroborate or something like that. Okay. And the compound is stabilized through resonance. Okay, so before we move to that, we can discuss about the naming of the diazonium salts. How can we name? Parent hydrocarbon plus diazonium plus anion name. This is a general formula for naming diazonium salt. What is the parent hydrocarbon? Parent hydrocarbon, for example, if it is C6H5, then this is aromatic diazonium salts, right? So if it is C6H5, that is benzene ring. So parent hydrocarbon is benzene. Then you have to add the term diazonium, then the anion name. Here in this example you can see 6H5N2 plus Cl minus. So parent hydrocarbon is benzene, anion is chloride. So the name is benzene diazonium chloride. Okay, we can see another example, C6H5N2 plus HSO4 minus. Parent hydrocarbon benzene, then diazonium, then anion name. Anion name is hydrogen sulfate. So benzene diazonium hydrogen sulfate. So diazonium is common for every diazonium salt. Then the hydrocarbon part and the anion part will change. Okay. So understanding this naming is important because it helps you quickly identify the structure and reactivity of the compounds further in this session. And diazonium salts are stable at low temperatures because of the resonance stabilization. Irene diazonium ion is stable at low temperature in between 273 to 278 Kelvin, and the positive charge delocalized into the aromatic ring across 4 resonance structures. So diazonium salts are stable compounds, but at high temperature they will decompose. They are not stable at high temperature. And as well, we have discussed in the previous video that primary aliphatic diazonium salts are highly unstable. They cannot exist, so they will decompose to release N2. So we have discussed about that. Okay, so basically we know aromatic diazonium salts are stable compounds. So that's about the structure and the naming of diazonium salt. Now we can look at the preparation of diazonium salts. So there are 2 steps. First is generation of nitrous acid, which is used as a reagent in the diazotization reaction, which is a reaction for the formation of the diazonium salt. Then the second step is diazotization of primary aromatic amines. So why we are generating nitrous acid in situ? In situ means within the reaction itself we are generating the nitrous acid, because nitrous acid is not stable, so we cannot store the nitrous acid. So we are generating nitrous acid in situ using NaNO2 and HCl. So NaNO2 plus HCl gives HNO2 plus NaCl. This is a reagent for the preparation of diazonium salt. Nitrous acid on treatment with aniline at 273 to 278 Kelvin, it will produce diazonium salt plus NaCl plus H2O. So this is diazonium salt preparation. So what is the temperature? It should be 273 to 278 Kelvin. Then reagents used are NaNO2 plus HCl. The key term used is diazotization. So this is the preparation of diazonium salts. Now let us understand the physical properties of diazonium salt, which give us insight into how they behave under different conditions. So for instance, benzene diazonium chloride. So what are benzene diazonium chlorides? Ca6HO5, benzene ring, benzene diazonium. Diazonium means N2 plus, then chloride, C6H5N2 Cl minus, benzene diazonium chloride. So benzene diazonium chloride is a colorless crystalline solid that is highly soluble in water. They are colorless crystalline soluble and they are soluble in water. It remains stable only in cold aqueous solutions, but if the solution is warmed or if the compound is isolated in a dry state, it decomposes easily. Got it? They are remain stable only in cold aqueous solutions. On the other hand, benzene diazonium fluoroborate. What is benzene diazonium fluoroborate to benzene ring? The anion is different. What is the anion? Fluoroborate. That is BF4 minus. So benzene diazonium fluoroborate behaves quite differently. It is insoluble in water and much more stable. Even at room temperature, they are stable. Okay, they can withstand the room temperature. But at the same time, benzene diazonium chlorates, they were stable in cold solutions, and just by warming they will decompose us, or by isolating to dry state also it will decompose us, so we cannot store. But at the same time, benzene diazonium fluoroborate, they are stable at room temperature. This stability allows it to be isolated and stored, which is practically useful in certain reactions like the Bose-Schimann reactions or some other reactions. So that is the difference between some physical properties of benzene diazonium chloride and benzene diazonium fluoroborate. Now we come to one of the most important parts, chemical reactions of diazonium salts. Broadly, these reactions are divided into two categories. First is displacement of N2, second is retention of diazo group. So we know the general formula of diazonium ions is Ar N2X. So in the first case, displacement of N2, nitrogen escape as gases and another group takes its places. So what is happening here? N2 escaped as a gas and another group comes and takes its place and forms a new compound. So there are totally different 7 reactions to study. First one is Sandmeyer reaction, then Gutterman reaction, replacement by iodine, then Bose-Schimann reaction, reduction by hydrogen, replacement by OH, replacement by NO2. So by looking at these reactions, you can see what is happening here. So N2 is leaving, and in Sandmeyer reaction, chlorine, bromine, they are taking its place. In Gutterman reaction, chlorine, bromine taking its place, replacement by iodine. Then Bose-Schimann reaction, fluorine is coming and taking its place, and so on. Okay, that is displacement of N2. So we will go through these reactions one by one. So before that, we can see the next reaction. It is retention of diazo group. What is happening here? NN bond is preserved. Product is an azo compound. The product is an azo compound. In this reaction, diazo group remains untouched, forming azo compounds that contain the NN linkages. Okay, these two categories form the foundation of all diazonium chemistry. So we will go through this in detail. Now let's begin with the displacement reactions, starting with the Sandmeyer's reaction. Okay, so first reaction is Sandmeyer reaction. This is a very important reaction where a cuprous salt acts as a catalyst to replace the diazonium group with another group such as chloride, bromide, cyanide. Okay, so you can see here cuprous salt, copper one. So for example, Cu2Cl2. This is a cuprous salt. Okay, where a copper atom is has +1. Each copper atom is in +1 oxidation state. Okay, this cuprous salt acts as a catalyst, and what will happen from the aryl benzonium salt ArN2X, it replaces the N2, removes the N2 and replaces by another group such as chloride, bromide, like that. So we can see some examples. So see, if using cuprous chloride, introduce a chlorine atom into the benzene ring. How can we do? This is a benzene diazonium salt. To that, in presence of cuprous salt and HCl, we can introduce chlorine to the aromatic ring. So N2X, this group is leaving and chlorine is coming, and we will get a chlorobenzene. If it is benzene group, Ar is benzene group, we will get chlorobenzene and N2 is released. Okay, while cuprous bromide introduce bromine and cuprous cyanide introduce cyano group. This reaction is extremely useful because it allows us to introduce functional groups that are otherwise difficult to add directly into the aromatic ring. So this reactants using the cuprous chloride bar HCl, we can get aromatic compounds to that chlorine is attached. Using cuprous bromide and HBr, we can introduce bromine to the aromatic ring. Using cuprous cyanide or potassium cyanide, we can introduce cyanide to the ring. Okay, this type of reaction is called Sandmeyer's reaction. Now a closely related reaction is a Gutterman reaction, which also introduces chlorine or bromine into the aromatic ring. However, instead of cuprous salts, this reaction uses copper powder along with hydrochloric acid or hydrobromic acid. In Sandweiss reaction, it was cuprous salts, but in Gutterman reaction, we are using copper powder along with halogen acid. This is an alternative method for introduction of chlorine or bromine to the aromatic ring. Although the mechanism is similar to Sandweiss reaction, the yield obtained in Gutterman reaction is generally very lower. So because of this, Sandweiss reaction is usually preferred in particular applications, but it is important to understand both for exams. So Gutterman reaction, what are the reagents? Copper powder plus halogen acid. But in Sandweiss reaction, it was cuprous salt as a catalyst. Right? Now we can see some example of Gutterman reaction. And one point is that this yield in Sandweiss reaction is better than Gutterman reaction.
When a diazonium salt
in most of the reactions
reacts with the
Sandweiss
copper and hydrochloric acid, it produces the corresponding
iodine
chlorine substituted
basically
aromatic
direct
compound,
hydration
and
of
end-to-end
benzene is
copper
not very
HCX is
effective.
also released
But
along
diazonium
with
salts
that.
provide a
Okay?
simple solution.
The same
When
reaction
diazonium
can be
salt
done
reacts with the
using
potassium
copper
iodide,
and
the
HBr
diazonium
to
group
get
is
the
replaced by
bromine substituted
iodine without the
aromatic
need of any
compounds.
catalyst. So this is very important reaction in synthesis because it is very difficult to introduce iodine. It refuses direct halogenation. Okay, but diazonium chemistry can avoid these problems simply without any catalyst. That is the important part. No catalyst needed. Nitrogen leaves as gases by reaction with potassium iodide. So aromatic diazonium chloride. So diazonium chloride on treating with potassium iodide, it is introducing iodine group to the ring, then releases into gas and KCl. Okay, this is very what is the reagent used? Potassium iodide. Product is iodobenzene, and there is no catalyst used in this reaction. Okay, now the fourth reaction is the Bose-Schiemann reaction. It is a very special and important reaction used to prepare aryl fluorides. To prepare aryl fluorides, we can use this reaction, and a direct fluorination of benzene is not practical, so this method becomes essential. So in the first step, what is happening? The diazonium salt react with fluoroboric acid to form a diazonium fluoroborate precipitate. Okay, this reaction is happening through two steps. First is that diazonium salt reacts with the fluoroboric acid HBF4 to produce the precipitate of diazonium fluoroborate. Okay, fluoroborate. Then what is happening next? In the second step, this compound is heated. Fluoroborate is heated. This diazonium fluoroborate is heated so that it will decompose and forms the aryl fluoride along with boron fluoride and nitrogen gas. So you can see the overall reactions here. Air into Cl, aromatic diazonium chloride on reaction with fluoroboric acid. It is producing the aryl diazonium fluoroborate precipitate, which on heating produces the aryl fluoride. Along with that produces boron trifluoride and nitrogen gas. What is the importance of this reaction? Aryl fluorides cannot be prepared by direct halogenation. Diazonium chemistry is the only practical synthesis route for this preparation. Here is the importance of Bose-Schiemann reaction. Now, the next reaction is conversion of diazonium salts into simple benzene derivatives by replacing the diazo group with hydrogen atom. So now we have discussed introduction of chlorine, bromine, iodine, fluorine, this type of compounds. Here we are going to discuss about conversion of the diazonium salts into benzene ring or some simple compounds, simple aromatic compounds. And here what we are doing, replacing the diazonium group by hydrogen. So this we can do by mild reducing agents such as hypophosphorus acid or ethanol. So what is hypophosphorus? H3PO2. Don't be confused with the terms phosphorus acid, phosphoric acid. Okay, so H3PO4 is phosphoric acid, H3PO3 is, I can write H3PO3 is phosphorus acid, H3PO4 is phosphoric acid. Here it is H3PO2. This is hypophosphorus acid. Okay. So on treating diazonium chloride, aromatic diazonium chloride with hypophosphorus acid and treating with water, it will produce benzene. Okay, if this is a benzene ring, it will replace the diazo group with hydrogen atom and produce the simple aromatic compound. Along with that, it will produce N2, H3PO3 and HCl. And like that, we can do this reaction using another reagent, which is ethanol. So treating the reagent with ethanol, we can introduce hydrogen atom to the aromatic compound, and along with that we will get N2 and CH3CHO ethanol. So what is happening here is basically we can say the diazonium chloride it is reduced using mild reducing agent. Introduction, we know that addition of hydrogen or removal of oxygen is reduction reaction. So here addition of hydrogen is happening. If this is a benzene ring, we got the simple benzene. Then at the same time the hypophosphorus acid is oxidized to, here addition of oxygen is oxidation. So hypophosphorus acid is oxidized to phosphorus acid. Okay. Now here this compound is reduced to benzene, the simple aromatic introduction of hydrogen. At the same time alcohol is oxidized to aldehyde. Okay. So this is replacement by hydrogen atom. The another important reaction is formation of
phosphorus acid,
phenol, okay, from diazonium salts. When the diazonium salt solution is warmed slightly above 278 Kelvin, it undergoes hydrolysis and the diazo group is replaced by a hydroxyl group, OH group. Okay, we can look at this reaction. The diazonium chloride, it is hydrolyzed just by heating at 278 Kelvin. It undergoes hydrolysis and the diazo group is replaced by the hydroxyl group. So hydroxyl group is OH introduced to the aromatic compound. So you will get the phenol. Initially you are taking a symbol diazonium salt benzene N2 benzene diazonium chloride plus which one hydrolysis. What we will get? We will get benzene ring, the IR group, then OH group is introduced. Right? OH group is introduced. We will get the simple phenol. Then N2 gas is also released and HCl is also produced. This is very simple reaction, right? So condition is that diazonium salt solution is warmed up to 283 Kelvin. Means that above 278 Kelvin we have to warm. Now the other reaction, the last and final reaction in the displacement of N2 category, it is replacement by NO2 group. Means we are converting diazonium salts into nitro compounds. The compound with NO2 group is nitro compounds through the fluoroborate, then aqueous sodium nitrate over copper. So we can look this in detail. This reaction typically involves the formation of a diazonium fluoroborate intermediate, okay, followed by treatment with aqueous sodium nitrate in the presence of copper. So first look at this benzene diazonium chloride. We are taking Ar(N2Cl), benzene diazonium chloride. We are treating with HBF4, fluoroboric acid, and so that we will get the diazonium fluoroborate. Here what happened? The Cl is replaced by BF4, fluoroborate, okay, plus HCl is also produced. Now after that we are treating with aqueous sodium nitrate in the presence of copper. Aqueous sodium nitrate in the presence of copper, and on heating what we will get? We will get the final product, that is nitrobenzene. Along with that sodium fluoroborate and N2 gas is also produced. NaBF4 and N2 is also produced. What are the steps involved? Benzene diazonium chloride on treating with fluoroboric acid, it produces the corresponding fluoroborate, diazonium fluoroborate. Then what are the reagents? In the step 2 we are adding sodium nitrate, along with that copper. On heating we will get the nitro compound N2 plus NaBF4. So this is the reaction where replacement by NO2 group, means we will get the nitro compounds. Now we are moving to the second category. retention reactions, where the diazo group does not leave the molecule. Instead, it forms a new bond resulting in azo compounds. So in these reactions, diazonium ion acts as an electrophile. This our diazonium ions, it acts as an electrophile and reacts with activated aromatic compounds such as phenol or aniline. They are para-directing, ortho-para-directing groups, phenol and aniline. So they react with the diazonium ion, and where diazonium ion acts as an electrophile, and they form the azo compounds. Okay. So the reaction usually occurs at the para position due to the steric anti-electronic factors and forming the compounds with an NN linkage that in between two aromatic rings. So they are azo compounds. So this reaction, we can see this benzene diazonium chloride on treating with phenol, it forms para-hydroxyazobenzene, which has an orange color, and on treating with aniline, it produces para-aminobenzene, which has an yellow color. So the reason of azo compounds are so important because of their color, and this type of reactions are known as coupling reactions. Okay, here as a result of coupling reactions, we are getting azo dyes. Dyes means they have colors. For these azo compounds, they have color. So the color azo compounds are so important. It is because of their color. So the presence of two aromatic ring connected to the NN group creates an extended conjugated system. What is conjugation alternative? Single and double bonds. So there is a double bond. So because of this, there is an extended conjugated system. This allows the molecule to absorb visible light, which gives rise to bright colors such as orange and yellow. So conjugated systems can absorb visible light so that it gets bright colors such as orange for the para-hydroxyazobenzene and yellow for the para-aminobenzene. So because of this property, azo compounds are widely used as dyes in industries, and making this reaction not just academically important but also industrially relevant reactions. Okay, so that is about coupling reactions. Now finally, let's understand the synthetic importance of diazonium salts. So these compounds act as a gateway to a wide range of substituted aromatic compounds, including aryl fluorides, aryl chlorides, aryl bromide, aryl iodide, which even do not need any catalyst, and no direct halogenation is possible for iodine. So these are very important. Then for aryl cyanides, phenol, nitroarenes, so we have discussed all these reactions, right? So many of these cannot be prepared easily by direct substitution reactions, but this makes diazonium salts an extremely powerful intermediate in organic synthesis and a must-know concept for both exams and higher-level chemistry studies. So now, to truly master this topic, you should be able to apply these reactions in multi-step conversions. For example, a question like converting 4-nitrotoluene into 2-bromobenzoic acid. So it requires a deep understanding of diazonium chemistry along with directing effects and functional group interconversions. So practicing such problems will strengthen your conceptual clarity and problem solving skills, which are essential for scoring well in exams. So if you guys have learned the beginning of this chapter and if you know some other concept, you can use this method for the preparation of 2-bromobenzoic acid from 4-nitrotoluene. By following these steps, you can produce 2-bromobenzoic acid. Now, as we come to the end of this session, remember that diazonium salts are not just another chapter, they are the central connecting point in aromatic chemistry. So once you understand this topic clearly, many other reactions and conversions will start making sense. So keep revising, visualize each step and practice regularly. So with the right approach, this topic can become one of your strongest areas in organic chemistry. So we have discussed all the topic, structure and nomenclature of diazonium salt, the preparation, important methods for the preparation, that is known as diazotization, then physical properties, then display. There are two types of reactions, displacement of N2, second one is retention of diazo group. In displacement of N2 we have learned 7 different types of reactions. In retention of diazo group, that is a coupling reaction which forms azo dyes, and last one, the synthetic importance of diazonium salts. Okay, that's all about this topic. So thank you for watching.